All right, so guys, this is it. The date today is the 17th, and the topic for your notes today is limiting reactant and percent yield. And guys, what you're going to find is that the and, remember how we've talked about sometimes the ands in your title are this, and they're unrelated? Guys, this is an and that is actually bringing stuff together. These two ideas are very, very closely related, and one actually leads to the other. Guys, it's funny, when you come back for AP next year, the math that we are going to do today is actually the math that we're going to do the very first day, well, the second day that we get back together as AP students. The last thing you're going to do is solve a limiting reactant percent yield problem just to get the stoichiometry back into our minds as we're getting ready for the AP year. So, guys, let me set the stage for you. Two separate ideas, limiting reactant, percent yield, but they're married together. Don't write this down. So guys, here's what we know. We know right now that when reactions happen, reactants lead to products. But guys, today we're going to ask and answer two important questions. Number one is this: at what point does a reaction stop? Guys, that's going to be question number one. At what point does a reaction end? And you're going to find out the answer is when we run out of limiting reactant. Then, guys, question number two is this: how much product should a reaction make? And the answer to that is percent yield. And this is also the calculation that we're going to do in lab on Wednesday. So again, first, when do reactions stop? And then second, how much product should we make? So guys, this is where you want to pick up taking notes as we talk about what are called limiting reactants. Oh, and guys, I get to show you the best analogy I think I've ever come up with. It's coming. So guys, what are limiting reactants? This is actually a no. This is a concept that you need to understand. So guys, let me define it for you. A limiting reactant is the reactant that is completely consumed in a chemical reaction. If you're the kind of person that benefits from detailed notes, this would be worth it. So guys, when we talk about limiting reactants, we're talking about the reactant that is completely consumed. So guys, let me just give you bullet number two, and then it all ties together. The reason we call this a limiting reactant is because it limits the extent to which a reaction can go. Once you're out of limiting reactant, you're done. Man, somebody cleaned out my goodie drawer. This is not cool. I know I can't do this without, well, here, I guess I could just use pliers. Well, I'll go in here. Guys, just a second. So, limiting reactant. The thing that runs out, the thing that limits the extent to which a reaction can take place. So guys, let me show you a simple example, and you'll never be wanting for understanding. So guys, what I'm going to do is I'm going to light this match on fire. And obviously that starts a reaction between the paper and the oxygen in the air. Guys, the question becomes, what then happens over time? So we allow the match to burn, and we know that it's not going to burn forever, right? That eventually this reaction is going to stop. And we know that it's getting close, and it gets down to the tweezers, and now it is done. Why did it stop? We ran out of paper, right? What does that make paper? The limiting reactant. So guys, now we need to talk about another important idea. This was a reaction with oxygen. How do we know that oxygen wasn't the limiting reactant? Because we're still alive. But guys, you understand that's how a lot of people die in house fires, right? They don't burn, they suffocate. Because the fire inside the house consumes all the oxygen in the house. There's no more oxygen to breathe and you suffocate. But guys, there's a name for that. So we understand that this is the limiting reactant because that's the stuff that went away. Guys, the other one is what is called the excess reactant. Here, I'm going to underline that. Guys, those are words worth knowing. The other one is what is called the excess reactant. And the excess reactant is the one that you have all that you need and more. So we've got limiting and we've got excess. So guys, this then leads us to a question. Obviously, when you burn a match in the air, it's super easy to figure out that you're going to run out of match before you run out of air. But guys, here's the question. What if it's not as obvious? What if you have a reaction that you're not familiar with? And what if you're not exactly sure then which one will be the limiting reactant? And guys, the answer is we figure it out mathematically. So please don't write this down, but guys, watch. In order to help you figure out how to figure out what limiting reactants are, guys, we are going to look at this reaction. Questions for you. What kind of reaction is this? You should know. What kind of reaction is it? One product, so it's this. What is the stoichiometric ratio in this reaction? 1 to 2 to 1 to 1. But guys, the question then becomes, what does this reaction represent? And guys, I know some of you are hesitating because you're like, this is stupid. This is fluorine, this is tungsten, this is sulfur, and that obviously doesn't make bismuth. Guys, this is not a chemical reaction, this is a recipe. And it is a recipe for building bicycles. Kind of. But stick with the analogy. So guys, we are going to claim that if you take one frame, two wheels, one seat, and you bolt them together, you get a bicycle. And guys, obviously that is way oversimplified, but it leads to a question. Guys, imagine that you got a job in a bike shop and your job was to build bicycles, but this is a cheap bike shop and they're building bicycles that are such low quality that instead of buying the bike and then assembling it, they actually buy crates full of parts. And so guys, imagine that you walk into the back of this room and they hand you a tool set and they tell you start building bikes. And in front of you are just crates of bike parts. And in those, you've got 120 pounds of frames, you've got 100 pounds of wheels, and you've got 50 pounds of seats. Here's the question. How many bicycles can you build? Or what information would you need to figure it out? Guys, talk to the person next to you. What information would you need in order to figure out how many bikes you can build? Talk about it. What information do you need in order to be able to figure out how many bikes you can build? Now guys, I want to follow up on what Jackson said. You said how much a bike weighs. What would you do with that information? Oh, wow. Okay, so if we have 270 pounds of parts, and say a bike weighs, let's use an easy number, let's say a bike weighs 10 pounds, you're saying we could build 27 bikes. No?
There's a possibility.
Okay, so maybe it would be like an upper limit, maybe? But guys, what information do we need in order to be able to get closer to how many bikes we actually can build? What do we need to know? Go ahead, Bruce.
The weight of
What do the parts weigh? So guys, let me give you this information. So guys, we're going to say, and these are really heavy, but guys, say that a frame weighs 20 pounds, and that a wheel weighs 10 pounds, and that a seat weighs 2 pounds. So guys, what do we do with that information? Well, what we do is we divide. And if we have 120 pounds of frames and they weigh 20 pounds apiece, how many frames do we have? 6. So guys, we've got 6 frames, we've got 10 wheels, and we've got 25 seats. Now talk about it. How many bikes can we build? Talk about it. Uh-oh. Now I'm hearing different answers. I'm hearing 5, I'm hearing 6, 25. You're going to have a bike with not many wheels. So guys, how many bikes can we build? It's not 6. Yeah, and guys, that's the problem. Now we need to respect the fact that one frame does not bind to one wheel, one frame binds to 2 wheels. So now we need to account for the fact that it's not a 1 to 1 to 1 to 1 ratio. It is 1 to 2 to 1. So we need to know the relative amounts that it takes to build a bike. So now when we do this math, we divide by these, and relatively now we have 6 frames, 5 wheels, 25 seats. Guys, which one are we going to run out of first? Wheels. What does that make wheels? The limiting reactant. And guys, what does that make the frames and the seats? Excess reactants. But guys, notice what we did. Bruce led us to one bit of information. He said, we need to know what the parts weigh. But guys, if this is elements rather than bike parts, we know what the elements weigh. That's the formula mass. So guys, the first thing we're going to do is we are going to account for mass. We do that with the formula mass. Then guys, we need to account for the stoichiometric ratios, because these don't bind together 1 to 1. So guys, we're going to do exactly the same thing here. How do we account for mass? Convert to moles. How do we count for the stoichiometric ratio? Divide by the coefficients. Guys, that becomes these steps. You might want to write it down. So guys, again, the idea is this. We are going to take, well, first of all, what we're going to do is we're going to write a balanced equation. Then we're going to take the weight of the parts. Just like the weight of the boxes of bike parts, we're going to take those weights and we're going to divide by the weight per part. And that gives us the number of parts. But guys, with chemicals, we do that with moles and formula masses. Then guys, we're going to divide by the coefficients, and then the smallest number, like the 5 wheels, will be our limiting reactant. So guys, I'll give you a second to write this down. We're going to solve one, then we've got one more thing to do and we're done. Can we go on? Still writing. That's fine. Did you guys like the bike analogy? Yeah, not bad. Oh boy, I love that. Look, we built bikes. You guys good? Nora, are you okay? Don't say yes if you're not. Promise? All right. So guys, it reads like this. I don't think you need to write this down, but guys, it's worth reading. So this is the reaction that we did when we made the hydrogen gas that blew up in lab last time. But now, guys, this gets a little different because now we've got 25 grams of HCl. We've got 25 grams of zinc. The question is this: which one are we going to run out of first? And guys, this gets even more complicated because we've got the same amount by mass of each one of the things. So guys, the first thing we need is a balanced equation. I would encourage you to write this down with me because guys, I'm going to teach you a problem-solving strategy. By the way, this is also the answer to calculation number 4 in your lab. Just saying. Maddie's looking. Did you get it? Did you remember subscripts? Yeah, so you got aqueous solid, aqueous gas. Like it. All right. So now, guys, let me show you a problem-solving process that makes these a lot easier. Start with mass over mass. Just trust me on this. This will make this so much easier. So 25 grams of hydrochloric acid, 25 grams of zinc. Now, guys, just like Bruce's question, which one of these do we have more of? By mass, it's the same. But we need to know what these things weigh so that we know how many we have of each in counting groups. So, guys, what we do is we convert to moles. And I just click through that because you know how to convert to moles. But guys, be careful of significant digits. So just like dividing by the masses of the frames and the wheels and the seats to find out how many frames and wheels and seats we have, we just divided by the formula mass to tell us how many particles we have, moles of particles. But guys, did you catch the relationship? Zinc is heavier, and therefore there are fewer of them. Just like bike frames were heavier than wheels. So guys, the idea is this is heavier, so there's less. So if we stopped right there, we would say, all right, we have less zinc, and therefore that's the one we're going to run out of first. But now we run into the problem that they don't group together one to one. So now, guys, what we've got to do is bring these coefficients down and divide by them. And guys, again, I'm clicking through these because I'm assuming that we can convert to moles together, and dividing by 1 and 2 should flow as well. But now, gang, the $10,000 question. You haven't answered the question yet. Because the question says, what's the limiting reactant? It doesn't say do math. It says, what's the limiting reactant? So guys, which number is smaller, top or bottom? Top is smaller. Top is the limiting reactant. Seriously, all you got to do is write a 5-word sentence. Blank is the limiting reactant. And you're done. So guys, what we'll do, well, not in here, but in AP at the very beginning of the year, is there's a whole lot more math we can do here. We can actually go back and figure out how much zinc is left over. We can actually go back and calculate the molarity of the zinc chloride solution. Guys, there's all sorts of stuff we can do with this, but for us, we're just going to identify the limiting reactant. So guys, if HCl is the limiting reactant, what does that make zinc? Excess. You guys good? Okay, so guys, that was thought number 1, limiting reactants, the logic, the calculations. Let's hit pause. Questions. Y'all good? Okay, so guys, we've got one more question to answer, and we are done, and this is called percent yield. So guys, let's do this. I hadn't even thought about this. This is what we just solved. But guys, let me explain to you the question that we're about to answer. So here's what we know. We know that HCl is the limiting reactant. The question is going to become this. When this reaction takes place, how much hydrogen gas should we produce? Guys, that's the kind of question that we're going to answer now and the question we're going to answer in lab. If we know that we run out of the hydrochloric acid first, how much of these products should we make? And then, guys, what we're going to do in lab is we're going to collect one of those products, weigh it, and then figure out how we did. And guys, that process is called percent yield. So guys, don't write this down. Don't write down the sentence. I want you to write down the math. So percent yield is a ratio, and it compares the amount of product that should be produced with the amount that you actually produced. And guys, the math looks like this. This is what you want to write down. Say that again. It's the opposite of percent error. So percent error is how much you got wrong. Percent yield is how much you got right. So if you watch my hands, remember percent error is subtraction, right? It's actual minus theoretical divided by theoretical. This is actual divided by theoretical. There is no subtraction. So it's the amount you got right instead of the amount you got wrong. Yeah, right? So guys, the actual yield comes from experimentation. How much did you collect? The theoretical yield is the result of a mass-mass problem. So guys, we're going to solve one of these. This is going to take us like 5 or 7 minutes. Excuse me. And then guys, you're going to have time to get your homework done. You're going to have time to work on the reaction types lab. Guys, it's going to be a good and productive day. And then guys, again, the calculation that we're about to do is the calculation that you're going to be doing in lab on Wednesday. This one's important, and it's the last page of the test. Guys, this is sort of our capstone, can you represent calculations moment in the year as we get closer to the end of the year. You guys ready to go? Okay. Reads like this. Oh wait, steps, sorry. So guys, the steps for these go like this. Write a balanced equation. I forgot about the steps. There's actually 5. So guys, you're going to write a balanced equation. Then you're going to start with a reactant mass. Then you're going to set your goal at the mass of what we call the known product. Then you're going to solve the mass-mass problem. And then you're going to use that in the percent yield equation. Adam, are you okay?
Yeah, all right.
I kind of saw you walking out. Are you good?
Yeah, I'm fine.
Okay. Yeah, it's interesting with as humid as it's been. Like, kind of. It's wet, right? I've had several students go like, oh, shoot. Yeah.
And I just get them like 5 months regular.
Oh, you do? All right. So, guys, once again, if you're the kind of person that finds steps supportive, comforting, guys, it goes like this. Write a balanced equation. Start with the mass of a reactant. That's going to be important. Guys, set your goal at the mass of what we call the known product. Then solve the mass-mass problem. Then use that mass as the theoretical yield in your percent yield calculation. So guys, we're going to do this. And then you're going to have time to get some good stuff done. You guys okay? Kevin, you okay? I'm more than happy to slow down. So many words. Quiet is a strange thing. We don't get much of it anymore. How about now? Are we good? You good, Nora? Good to go? All right. So, guys, consider this. I would encourage you not to write it down, but guys, I would strongly encourage you to write down the solution process as a model. So it goes like this. You've got 15.5 grams of Bunsen burner gas, methane. Obviously, you've got all the oxygen you need, because if you didn't, we would die. And guys, when we burn up all of that methane, imagine that we collect 32.1 grams of water. The question is, how did we do? Is 32.1 grams like really good? Or did we lose half of the water we created? And guys, that is the question that percent yield allows us to answer. We know how much went in, we know how much came out. The question is, how much did we lose? And guys, it's actually how much did we collect compared to what we should have. But guys, that's percent yield. Step number 1, balanced equation. I would encourage you to write it down. Guys, as you're looking this over with the idea that the test is on Friday, maybe as you're looking this over, you're also engaging at the level that says, this is a hydrocarbon. Oxygen is diatomic, so it gets the O2. Your products are carbon dioxide and water, because that's always the product of combustion, and then you balance it. So guys, with that said, watch. Just trust me on this. It's going to make your life so much easier. Once you've got the balanced equation, go back to the sentences, find the masses, and write them down. So guys, 15.5 grams of CH4. Write it down underneath. But then guys, this is where this gets a little trickier than the stoichiometry problems we've solved before. We also have 32.1 grams of water. So here then becomes the question, which mass do we start with? The mass of the CH4 or the mass of the water? And guys, if you look at the steps, what does it say? Always start with the mass of what? The reactant. Guys, one of these will always be a reactant and the other one will always be the product. Specifically, this is the mass of the limiting reactant. So guys, this is how we set this up. Ready? Watch these are good. Check it out. Here we go. So guys, set up a dimensional analysis bar and then watch this. We're ready? We're going to start with the mass. Come on, that was pretty good. The mass of a reactant. So bring this down. Now guys, we need our goal. And our goal is going to be the mass of what we call the known product, because that's the product that we know something about. Now guys, at this point, I hope this is okay. I'm going to click through this like we know it, because now we're solving a mass problem. So our first step is grams to moles. Hydrogen is 1.0. Should be 1.01, but we can round off the 4. If you put 16.04, that's fine too. So guys, 16 grams is 1 mole of CH4. Then at that point, guys, it's the mole-to-mole ratio. There's a 1 in front of the CH4 and a 2 in front of the water. And then, guys, our last step, moles to grams. So, gang, at this point, we just do the math, and I'll do it for you. It works out to 34.9 grams. Now we can start to get a sense of where we're at. So how much water should we have produced? 34.9 grams. How much water did we produce? Only 32.1 grams. So guys, we lost about 2 grams of water. So then the question becomes, okay, how is that as a percentage? So then guys, we write down the equation. Percent yield is equal to actual divided by theoretical. Then throw down the equal sign and draw a line. All right, you ready? Guys, what is our actual yield? Well, our actual yield is 32.1 grams, so bring it down. Then what is our theoretical yield? And guys, our theoretical yield is 34.9 grams. See how those fit? Then do the math, round to 3 significant digits, and guys, we collected 92% of the water that we should have. And guys, again, this is the calculation that you're going to be doing in homework, but then in your lab as well on Wednesday. Questions? Yeah?
So when you say collect the water, we should have the other, like, 2.5 grams.
Yeah.
Somewhere else, it's just that we don't collect that.
But here's I wanted to talk with you about this because this gets really interesting in lab. So yeah, we lost 2 point something grams, right? So we lost those 2 grams. So a question that we could answer is, where did it go, right? And we could talk about that. Maybe something leaked. Maybe you didn't use up all of your methane, something like that. But here's another interesting question, and this is going to be on the conclusions of your lab. So guys, join me for just a minute. Guys, what does it mean if this number is 100%? You collected everything you should have. But guys, what if it's 110%? Magic. You messed up. Guys, why is 110% not a valid answer? Go ahead.
Produced more product than was even possible given the basically violated the law of conservation of matter.
Yeah.
You ended with more matter than you had.
Right, you became a god, right? Yeah, you made matter.
Or you did your math wrong.
Or,
Two options.
no, there's actually another option, and you need to think about this, because guys, I'm going to tell you right now, almost half of you are going to get higher than 100% yields. So how does that work? And it was actually Nate or TJ that said it well. You messed up. But guys, it's going to happen. And this is something that you're going to have to think through during the lab. So guys, the bottom line is yields above 100% are impossible because you can't create matter. Adam's point. But guys, when that does happen, math is not the answer. Because if you're making math mistakes, that's just stupid. Right? So the answer is more to what Nate and TJ said. You messed up. And the question for you in lab is going to be, where did you mess up? You're going to have to find it. And that's part of the lab. It's called error analysis. And we're going to do that on Wednesday as well. Yeah?
In this case,
Mm-hmm.
it was like 100%.
Mm-hmm.
Yeah, you could have used too much methane.
Yeah, you could have used too much methane. Frankly, one of the big problems is impurities in your products. That's a big one too. Yeah. You guys good? Grab your homework packets, y'all. We are, wow, guys, done with new material for the unit. So we are now on, guys, homework assignment, and watch this close. You're on homework assignment number 4, which is not the last homework assignment in this packet. So guys, homework assignment number 4, you have 7% yield problems to solve. On the back, you have 2 limiting reactant questions to solve. Then guys, following that, you'll notice that it says additional practice. And guys, this additional practice includes writing and balancing equations. And then on the back, there's a couple limiting reactant problems you can work on as well. Guys, the answer to this additional practice, wait, is that the same one? Oh, guys, that's not even supposed to be there. I don't know why she did that. The limiting reactant problems on the very back are the same as the ones that are on the current homework assignment. But guys, at the end of the day, you can find the answers to these additional balancing equations things if you go to our calendar and go back to March. And when we learn to balance equations, doing reaction types, where did it go? Oh, here it is. Oh, nope. Here it is on the test. So guys, on the day of the test, it says reaction types, additional practice. Here's the assignment, and then the solutions to it. So you've got that as well. So guys, on Wednesday, we're going to turn in this homework assignment. We are going to turn in the reaction types lab. We're going to do a lab. That lab will be due on Friday because it's the last page of the test. And guys, you now have 30 minutes to work on your labs, work on your homework. I'm super available to you. I'd love to help. And guys, let's get some good work done. Go get 'em.